Okay, we have a long infinite cylinder. It's a coax, so there's an inner conductor and there's an outer conductor. Current heads one direction on the inner conductor, the other direction on the outer conductor. And we've got a geometry here where we know R1, we know R2 out to here, and we know R3 out to here. And we're asked to evaluate the magnetic field at a point that is between R2 and R3. Let's pretend I drew a circle there, right? So if this is a circle centered on the axis, then we can take advantage of certain symmetries, right? We know because it's infinite, you can't tell anything about where you are around it. Because it's at rotational symmetry, you can't tell angles. And so the magnetic field around this circle has to be the same everywhere, right? Well, if we look at Ampere's law, right? Right, the integral around that circle of B dot dl has to be equal to mu naught I, where I is the total enclosed current, right? So integral of B dot dl equals mu naught I. Well, B is constant along that circle, so we're just integrating dl around the circumference of a circle, and so we get, for the left-hand side, B onto 2 pi r, right, is mu naught I enclosed. And the hard part now is figuring out what's the enclosed current. You got a couple of clues here. One is clearly the central conductor is completely enclosed, right? But the outer conductor, you've only enclosed a portion of it. So what portion of it have you enclosed, and how do you figure that out? Right? All right, so, and we have here this assumption the current is uniformly distributed across the cross-section, right? Uniformly distributed. So what fraction of the outer conductor is enclosed? Well, if we look at the area of the outer conductor that's enclosed, it's going to be a circle of radius r, pi r squared, right, minus the area of pi r2 squared. And what fraction of the whole is that? Well, that would be pi r3 squared minus pi r2 squared. Think about that for a moment. So what is this? The fraction enclosed is a circle, right? Get some drawing tools up here. The area of a circle of pi r squared, right? Call that a circle, minus the bit in the middle, right? Because that's not part of the conductor, divided by the whole area all the way out to the outer ring minus pi r squared, pi r2 squared, right? And of course you can see the pi's all cancel out, and so this just ends up being r squared minus r2 squared divided by r3 squared minus r2 squared. So that's the fraction enclosed, and if you want to get I enclosed, all right, I enclosed is going to be I, the central conductor. You got that completely closed. Now the outer one is headed in the opposite direction, so that's also I, but onto this ratio, right, to get us to there. And you can play around with that algebraically if you want or not, but we've gotten to let's play around with it a little bit algebraically. I onto 1 minus, right, R 1 minus that ratio. All right. And so you can calculate this at this point. You know mu naught, you know 2 pi r. You can get the magnetic field from all of this. From B is mu naught over 2 pi r onto I enclosed. All right, and there you go. B is mu naught over 2 pi r times I onto all of that. And that gets you the magnetic field due to inside this conductor, assuming it's uniformly distributed. Now, let's look at this a little bit. What happens when R goes all the way out to R3? Well, this second factor here becomes a 1. You get 1 minus 1. And so out here, once you get out to the surface, you've got I and you've got minus I, and you have no magnetic field at all, which is the whole point behind a coaxial circuit or coaxial cable. The other limit is you take R into R2, so you're not enclosing any of the outer conductor, and you're right here at this inner edge. This second term goes to 0, and everything depends on just that inner conductor. So whenever you have a problem like this, it's useful to think about what happens at the boundaries just to see if it lines up with your tuition. That's it for this problem.